Welcome to our May meetup, not our April meetup. Thank you everyone for taking the time to join us today. The Open Source Satellite Programme holds regular meetups across a wide range of topics related to the space industry, from applications through to modelling, technical topics, hardware related, and broader wide space ecosystem topics. We have established the Open Source Satellite Programme with the vision of making an open source satellite to make space more accessible to the community and to promote responsible and sustainable utilisation of space. Through the team's own personal experiences within the industry of designing, building, operating and delivering spacecraft, we have seen at first hand the utility of small satellites and the ideas and markets that they have stimulated and the value they bring to many sectors and industries. And we can see this trend continuing into the future, where the potential for small satellites to influence and make a positive impact on everyone's lives is phenomenal. So the Open Source Satellite Programme has been developed for an open source community by the open source community. And so if you want to get involved, I'll tell you more about that later. In the last few sessions, we talked about technology and modelling methods, and today we're moving on to a slightly more hardware-related topic, and we're delighted to introduce Dr. John Paffett, the inspiration behind the Open Source Satellite Programme. And John's going to talk about OSSAT-T, a satellite testbed, and I'll let him go on and introduce and talk about it. So over to you, John.
Perfect. Thank you, Catherine. And welcome everybody, and good afternoon or evening or morning or wherever you are. So I know we've got lots of people from lots of different parts of the world. So as Catherine said, well, I'm going to talk about one of our sort of side projects today, which is the OSSAT-T, and give you a bit of an insight into what we're doing there, and also talk around sort of some of the challenges and problems we're trying to face. Before we start, for those that don't know me, so I'm John Paffett. I'm the founder, managing director of KISP, and the sort of chief architect and evangelist, as it were, for the Open Source Satellite Project. I've been in the space industry for over 30 years, very much on the sort of spacecraft manufacture side. My background is electronics, largely on the digital side, but a little bit on receivers. So digital signal processing on board computers, agile receivers. My PhD, just dim distant past now, was in orbit spectral monitoring. So very much interested in sort of the techie parts of things, and definitely driven by trying to stimulate the utility and application space, as it were. So now we talk a lot around the open source satellite related projects, but I thought it's just worth touching upon KISP and some of our activities, because actually that dovetails nicely with the rationale for this particular project. So we're a program and systems engineering company, and we're really driven by that desire to make space more accessible and stimulate the use and application, or as I'd like to put it, the sort of responsible, sustainable use and application of space. So we cover a whole heap of activities, really, from the training and development side. So we're partnered up with a group in the US called Teaching Science and Technology, Inc. So they're the guys that wrote the Understanding Space books and SMAD, Spacecraft Mission Analysis and Design. So we do a lot of teaching and training to industrial groups, companies, institutions, so European Space Agency, the US, JAXA, a range of different groups. And so that's one end of the activities that we're doing, all the way through to subsystem equipment, satellite manufacturing type activities, through to working with people on some of the downstream applications. So we've got the team tied up at the moment on one of the projects that's going through PDR, looking at infrared type imagery. So we cover quite a spectrum of activities, really, and a lot of program and system engineering related activities. And the reason why I mention that is that it sort of starts to put some of this into a bit of context, really. So where did OSSAT-T come from, or where was the sort of genesis, or the idea for OSSAT-T? And so through all those activities that we've been involved in, and many others actually, we've seen this growing demand or growing requirement for what I'd call a functional representative model of a satellite. So something that looks and behaves very much like a spacecraft, something that's had the same interfaces, something that behaves and works in the same way. And so we've seen that, whether that's with the clients that we're working with, or even with our own team as we grow the team, recruiting in, for example, a software engineer, having that person have a good understanding of how the spacecraft works and how their software fits within the spacecraft is really valuable and really important. And so we wanted something, and we see the need for something that we can use for teaching. So teaching spacecraft and system engineering, for example, something we can use for training. So as mentioned, training of staff or partners on spacecraft engineering, and also something that we can use for a test bed. So something we can use, for example, for developing the algorithms and the software that we're going to use on the open source spacecraft, or for as a prototype, or for prototyping up payloads, for example, or for trying out new interfaces and equipment. So we wanted something that was quite versatile that we could use for a range of different activities. And we wanted something that we could actually use as a sort of stepping stone. Something that we could use on a stepping stone on that development path for the open source satellite. So that's really what was the genesis of why we wanted to do it. And so we made the decision to basically get on and develop the open source satellite, or the OSSAT-T space systems engineering testbed. So the goals, and I've touched upon some of these already, was really to come up with a functional representative model. So something that was close to a spacecraft without it being the spacecraft itself. We wanted it to share common elements with the OSSAT. So things like the onboard computer, things like the software, so that it really was as close to that final spacecraft as we could make it, so that as we're developing and prototyping and working with it in the lab or in the classroom, it's easy to see that transition to taking that into space. And I'll come back to why I think that's important in a minute when we look at some of the other development platforms that are out there. The other thing that we want to do is make it accessible. So make it accessible to the widest community. And partly that's by minimizing the cost, trying to get the price of it down. But it's also through things like making it available on the online store and opening up the design so that it's open source in its own right. So really getting it out there, publishing it, and making sure that it's accessible to all. So those are really the key goals that we had in mind as we moved out with the development. Now, before I actually come back to the OSSAT-T, I'm just going to sort of go off on a bit of a tangent, really, and talk around some other topics. And one of the key ones is sort of rapid prototyping. So if I think back to when I started tinkering around with electronics quite a while ago, everything we started was sort of started from scratch. There was no internet, there were no repositories of data, there were no example sheets. You really were starting from scratch. And you were buying in resistors and capacitors and integrated circuits and transistors, and you were building the designs yourself, very much from raw components. Fast forward a period of time, and it's become so much more accessible with companies like SparkFun, Adafruit, Pimoroni, even Farnell and RS and the sort of classical distributors all selling some of these breakout boards and hats and shields and things. So it's become a lot more accessible, and there's reference designs out there and examples really at people's fingertips that you can take and use very, very quickly. So you can go from an idea in your head and have a prototype of a design up and running incredibly quickly. Which is brilliant. That's excellent. It just makes it so much more accessible, which is great. And you no longer, as I say, have to start from first principles. So now, if you want to know how to download data from an aerospace craft, you can just go and Google and you find it in Instructables, and somebody's done something that you want to do or something similar that you can then use and build upon as you see fit, which that's phenomenal. And it's incredibly accessible. So I put this example in because we're actually working with the Spaceport Cornwall team on the design and manufacture of a small environmental monitoring spacecraft, KernOSSAT-1. And KernOSSAT is a marine environmental monitoring spacecraft. But part of the real drive of that program is to demonstrate the linkage of space into the community. So it's making a spacecraft that is very, very relevant to the local community. And Cornwall's surrounded by ocean, so what's more relevant than the sea. And so we're working on this program that's actually able to collect marine environmental data from buoys. And so we're working with Truro Penwith College and Exeter University to develop payloads that will be floated out on buoys or on boats, and the satellite will then collect the data. But the other thing you can do, and this young lady is a great example, she came up with the idea of doing a similar thing. And so she went out and she bought the various different components from, I think she was buying them from Amazon, and actually prototyped up a little ocean monitoring buoy over a period of weeks, and basically blogged all about it and put it out on Instructables, and that's just phenomenal. You know, you can take an idea and implement it and get it out there, which is great. And the fact that she then went on and shared it with everybody is really brilliant. So we're trying to do a similar thing in Cornwall with a local community and get this out into the playgrounds and out into the schools, so that we can really just encourage people into engineering and science and technology. So it's phenomenal. So it's some real good value. And it's not just about the equipment either. It's not just about the availability of breadboards and breakout boards and components. It's actually some of those tools and equipments that can make rapid prototyping really an easy thing as well. So, you know, great example, we had some spin turns in last summer that were looking at some power system elements. I don't know if many of you on the call have manufactured electronic boards at all, but I sort of explained the sort of electronics design game really is a hurry up to wait, because you spend a lot of time designing your board, and then unless you want to pay an absolute fortune for next day delivery, you send it away, and then 15 days later your board comes back, and then you find out you've got a mistake, so you wait another 15 days. With this instance and the use of a CNC milling machine, we're able to very rapidly basically come up with the design in one day and have it milled out the next day or the same day and populated, and that gets us moving with some of those designs really quickly, which is great, or can be great. I'll come back to some of the pitfalls in a minute. So, but it all makes it much more accessible, much more readily available, much more quicker, which is got some good benefit to it. I say that though because there's also a sort of cautionary note, as it were, and it's worth really touching on what I call the good, the bad, and the ugly, or the good, the bad, and the really bad. So the good bit, and I've talked a lot about the good bits, is very quick and efficient to get something up and running. So that's great. The bad, well, sometimes speed results in rushing, and that's when you start making mistakes. And I'm just as guilty of this sometimes. You know, you think, well, I don't need to think about this. I can just get the boards and throw it together. And then you spend an absolute long period of time trying to fault find and debug something, because if you'd have only taken a deep breath and thought it through in the first place, you wouldn't have made some of the silly mistakes. So you really got to, you know, it doesn't substitute the need to do some design and think about what you're going to do before you get on and do it. The ugly is actually, you can, if you're not careful, lure yourself into a false sense of security and even abandon basic engineering principles. So I've seen, you know, I've seen people that are prototyping things up on a desk, and they'll go, well, it works, and then they'll put it into space to find out that it doesn't work. And it's because they've not even thought through the design, and it just happens that the right size of the cables and some of the levels on the power supplies were such that the interfacing between certain boards was marginal, but it didn't show up on the bench. But when they eventually got into orbit, the levels were all incorrect, or the interfaces were all wrong, and so funnily enough, it didn't work. So although it's a really quick thing, and there's some real benefit in doing it, you know, it doesn't substitute the need to do the underlying engineering in the first place, and that's where there's sort of a cautionary note and some care and attention that needs to be taken into account. And why am I talking about this? You'll see in a minute when we start looking at some of the other test and development environments, how if you dumb things down or make things too simple, people think that's the extent of the problem. They don't think about the other things that you need to do in order to make sure you've got a very well engineered solution. So now moving back then to some of these development, or some of these other development platforms. So there's a number of different satellite development platforms out there, or simulators, or teaching aids, or training models. And the sorts of things I'm talking about, you know, if you go and talk to a satellite manufacturer, so whether that's an SSTL or a Clyde Space or a TIVAC, you know, you may be able to buy a flat sat. So basically an electrically representative model of that spacecraft, and use that for test and demonstration, or test and verification, or test and development purposes. So that's one extreme, and I'm not really going to touch more upon that, but there's a picture of Clyde Space One that they supplied to the UK Satellite Application Catapult for the IOD program. The three that I'm going to talk around is another satellite application catapult project called the UBO. ISSAT, so that's a classroom spacecraft that TSTI and ourselves and many others actually been using for many years for doing design validation verification type classes. I'll come to something that we've been working with TST on recently called the EssentialSat. So that's a system engineering learning laboratory. And then after I've talked about those platforms and some of the pros and cons, we can come back and talk further about the OSSAT-T. So one of the real quandaries or the challenges is how do you take a complex problem? So designing a spacecraft and tailor the way that you communicate that in such a way that you make it understandable or relatable to the audience you're working with. If you just bombard them with all of the challenges, they just get demotivated and they don't want to go anywhere. So it's how do you convey the information or convey the content in a way that enables you to sort of bring people along on that journey. And the maker community has done quite a good job at doing that in terms of starting to identify things that are sort of basic tutorials and more intermediate tutorials and more advanced type tutorials. So it's just trying to provide the context in which that particular thing's working. And I'll give you a couple of good examples in bits of hardware we've got here. So how do you do that in such a way? And for me, partly that's about sort of striking that balance. So it's about tailoring or targeting what you're doing to a given audience. But even that comes with some challenges because you've got to sort of set out the boundaries. And also you've got to try to find a way of avoiding some bad behaviors. And, a great example. So I've got one of the satellite application catapult UBOs here. So this is great. So here we have a tiny sort of pocket cube type spacecraft. So if you've never done anything in space before and you look at the literature that they've generated as well, and you go, wow, I can build a spacecraft, and very simple, quite small, it's got solar panels on for generating power. It's got a small camera for taking an image. In fact, you tilt it, it takes an image, and then you can download it to the computer and get a selfie. It's a glorified selfie stick, really. And if you remove one of the panels, you can see the batteries, you can see the computer. It uses a little Arduino. So that's one of the things about sort of making stuff relatable is this particular one has software that runs on an Arduino. Quite a lot of the community use Arduinos for other things. So it's a software development environment that is known to them and is understandable. So you go, well, that's great. The downside is, and this is one thing I don't so much like about their site is they talk about this, and then in their list of things you can do is launch it. Well, actually, the sort of utility of this size of spacecraft is limited. There are some applications, but you have a spacecraft there that is actually really difficult to detect with today's radar systems. So you take this and fly this at 600 or 700 kilometers, 400 kilometers, very difficult to observe. So there you've got an object whizzing around in an orbit that you can't move in order to avoid another space object that actually, if that was to hit you, it would wipe your spacecraft out. So some interesting challenges. The other thing that this doesn't really teach very well is systems engineering. So there's almost this view that you can take a number of sort of pieces of equipment and maker pieces, bolt them together, throw them into orbit, and that works. And that's where problems lay. So it's really sort of striking that balance. So say UBO is the first example. This is the material that they've done in putting this together is really brilliant and great for classroom activities. And the whole idea of this, and that's where the title came from, actually, is to understand, to build, to operate a small spacecraft, and it does that really well. The documentation that's with it, the stuff is great, and it's good as a sort of an entry level, very basic type of capability that gives a first insight to space and gets people enthusiastic. And just, here's a link to their website and a little bit of a snapshot of their build instructions. That's pretty cool. And they've done a couple of pilot classroom activities with across the world, actually, in a number of different places. So it's been great from that perspective. Another one, and unfortunately I've not got one of these that I can show you today, but we work with a group in the US for OSSAT. So I mentioned this is a classroom satellite training model that we've been using for satellite design, validation, verification courses. So it's a functional representative model. It's got many of the subsystems and equipments that you find in a satellite. It allows you to do experimentation in the classroom and give people a hands-on experience to the sorts of subsystems and equipment that you would find in a spacecraft, and allow you to sort of experiment. Now, when you look at that, you see, well, it's got all the parts, but it's not quite a spacecraft. And one of the challenges with this is it's good, it's just quite expensive. So if we want to have a class with 5, 6, 10 of these in the class, they're about £10,000 or $12,000 a piece. So it becomes quite expensive. It's not the sort of thing you can easily leave with a class either. And so, we've seen the need for something slightly different and a different price point, which I'll come to with the next. So say we basically learning the lessons of things like the UBO and what we've been doing with OSSAT. We set the challenge and said, well, we need something, an alternative teaching aid. So something that is representative of a satellite. Again, it's another functional representative model, has many of the similarities or read across from things that people are used to. So again, this is based, and this is a prototype of it actually. So the onboard computer that we're using here is based upon an Arduino. We wanted something basically that when the students and not meaning just school and college students and university students, actually we use this out in industry, but when it gets broken, that we can easily substitute the parts for commercial off-the-shelf boards. So this based upon an Arduino-based data handling unit and an Arduino-based AOCS controller, and this enables us to sort of demonstrate many of the functions that you'd expect to see in a real spacecraft. There's a reaction wheel in here. This will, and I was hoping to get the demo up and running, but a few issues earlier, but not with this, but with other things. But basically, this will do sun tracking. So basically, we can dangle this on a stand. We can get a torch and have the satellite track the sun, which is great. So it starts to get us a bit closer to what a real functional spacecraft would do. This particular one has an imaging payload as well, so a slightly bigger camera than we've got on the UBO, but it enables us to start to explain things like how the operating system works and how we capture the data and download the data at the same time as we're receiving telemetry and being able to send telecommands up to the spacecraft. So it gives us a good platform that we can use, and you can see on the image here in its sort of classroom configuration with a laptop and the platform, and that's working pretty well. So we've just finalized the prototyping of that, supplied a couple, and just in the process at the moment of building the next batch, so getting to a point where we've got that sort of mature baseline product that we can use moving forward. So that's quite exciting. And here is it again in a couple of different configurations, where we had in a sort of flat sat configuration earlier in the year in the lab, through to sort of an earlier prototype of the model there as well. And there's just a little picture of the ground support software. So this is basically the GUI for looking at the telemetry on the spacecraft, and we use a piece of software that Tim's written called Scotty for that, which again gets people used to sort of the hands-on of being able to operate and control a spacecraft, and really understanding how their part fits within the context of that broader spacecraft system design. Yeah, sorry, that was going to be my demo. So that's Essential Sat. So what we've just seen there is an interesting sort of spectrum of different solutions, really, going from the ISSAT as a sort of an entry, the UBO as sort of an entry level capability, with increasing levels of sophistication up to, say, what we're doing with the OSSAT. When you step back and go, well, just how flight representative are these? Well, yeah, I agree. There are people that are launching pocket cubes, so this sort of form factor. But when you start thinking about the real utility and application, or the operationality of such a satellite, it's I would say this is not it's not fully flight representative at the moment. So it's difficult to impart all of the knowledge and the understanding of what you need to do on a larger size of platform with that particular product. When we get up to things like the essential sat, again, you're getting closer to it being flight representative, but there's some elements in here that you really wouldn't do in flight. It's I talk about things like the Arduinos. I remember back a long time ago talking to Chris, who then went on to found Planet Labs. He, at the time, was working for NASA Ames and had developed PhoneSat. So he was talking about flying a mobile phone, or in fact did go on and fly a mobile phone. And they were going on about how brilliant that was at flying a mobile phone. Well, that's good. But I think brilliance is actually recognizing that within that mobile phone, it's not the mobile phone, it's the chips inside it that's useful. So the brilliant part would be going, actually, I want to use the processor out the mobile phone, because that processor out the mobile phone has the capability I need. It's manufactured in the billions. It's got a really intrinsically high quality level. It's low cost, readily available, although not today, with the global chip shortage we have as a result of the pandemic. But once it's settled down, COTS devices are normally quite readily available. The problem is when you start looking at flying a mobile phone, for example, or when you start looking at flying an Arduino, or when you start writing software and putting in lots of bells and whistles, one of the challenges that you've got is you're designing stuff into your spacecraft that is increasing the level of risk. So, if all you really want out of this is the main processor, the fact there's other chips in here that might get affected by radiation and might latch up and might wipe out the onboard computer, well, that's not so smart, is it? So it's really just sort of stripping it apart and go, actually, what's the bare minimum and essentials that I need inside my spacecraft so that it is robust and reliable and resilient. And so that's one of the reasons why we start looking at things like, flying the Arduinos and go, well, actually, it's not about flying the Arduino, it's about flying the core underlying processor and then having more control over the software. So you'll see in a minute, one of the things that we're looking at is using the same computer in the OSSAT-T that we're then going to go and use in the open source satellite. So what did we want from the OSSAT-T? We wanted a modular platform that we could use for, let's call it, intermediate and advanced users. So I do want something that maybe we can use the Arduino IDE on for intermediate users, but I also want the ability to not use that and to be able to use the flight software for the open source satellite. I very much sort of subscribe to the test as you fly. The more you can be testing in a flight representative manner, the more likely you are to iron out all the issues you're going to have when you then eventually launch a spacecraft. And so we wanted this modular design. We wanted something that, say, was functionally representative. So it doesn't have to have all the same components. So, great example. we want to have, so this is just a structure model actually. And this is first sort of iteration of a structure model actually, but here you see a big payload bay in the top. So we're thinking about, one of the baseline payloads in here would be maybe a Raspberry Pi with the high def camera and a lens. So that enables us to sort of explain how payloads work and show the interfacing and all those elements. But at the same time, maybe we don't want that payload. Maybe we want to put a small communications payload on. So the ability to be able to chop and change and to be able to adapt and vary things is quite key. Another thing. So when we started doing some early, this is a really early prototype when we were looking at AOCS. So this is a reaction wheel system where we were developing some of the algorithms and using Simulink, so we could do Simulink algorithms and be able to do autocode generation to then plant it onto the host processor. So with this one, we were just using a simple DC motor. under sort of essential SAT, we've moved across, if you probably see on the bottom here, but this is a stepper motor. In fact, this one's probably easier to see. So that stepper motor driven sort of reaction motor. But one of the things that we're sort of keen to be able to show as well as there's a brushless DC motor. So that's a lot more representative of what we'll have flying in the eventual spacecraft. And in fact, for many of the programs we're doing, we wouldn't fly with a single single motor, single wheel. So actually being able to take out the reaction wheel and putting in a 3 or tetrahedral type wheel configuration, which is much more representative of a final spacecraft, that enables us to cater for the sort of advanced applications, as it were. So it gives us a bit of modularity, it gives us a bit of scalability. So that's sort of the goals on that. The elements of the system are very similar to you see with everything else. I mean, what we're trying to do, as we've done with the open source satellite, is keep a clear delineation between platform and payload. And so on the platform subsystem sides, there's obviously the attitude control, the data handling, the telemetry and telecommand subsystem, electrical power system. And then thinking about the payload as being separate. So whatever the payload, the instrument or the sensor is, some form of payload controller, and even putting a payload transmitter. So the baseline configuration that I'm looking at for here is sort of UHF for TTC, and then put an S-band downlink on for the payload data. So then you could use the power system to turn on the payload, the camera and the computer, take an image, store the image, process the image, and then download, turn the transmitter on and download the images you get in the ground station. So you're starting to be able to really demonstrate the ConOps for how that spacecraft will work. And going back, so I mentioned about sort of the functional representative model. So it's not all flight elements. So I think on the computer, we're planning to use the same process that we're using on the open source spacecraft. But when we look about things like the power system, we want to have power switches, but we don't necessarily need the cost of the MOSFETs that we're going to use in the flight spacecraft. We can use something much more simpler and much more cost effective for the development platform, because it demonstrates the same functionality. It's not the final solution, but it gets us that much closer. So they're the main elements. And I mentioned the sort of Raspberry Pi type camera payload. So that's great because it enables us to start to explore and demonstrate some of the other capabilities and functionality you need to put in place for things like a small Earth observation mission, which is good. So and it's trying to pick things that take us on that path closer and closer towards the open source satellite platform. So with the onboard computer, having something that has the same processor, the same memory type, some of the same interfaces. So putting a CAN interface on, for example, so that we can have somebody starting to develop a CAN payload and be able to use the training model in order to get their payload task up and running, or to demonstrate how a particular element of the payload processing works, gives us that flexibility. But obviously there's some elements that we would have on here that we wouldn't be flying. So debug LEDs, for example, or access to status LEDs, or a reset button. Once you've got this spacecraft in orbit, you're not going to go up there and press a reset button or do a Control Alt and Delete. It's up there for good. You've got to be thinking about fault detection, isolation, recovery, for example. So really getting people into that mindset, the system thinking of what they need to do to make sure their spacecraft is going to operate in the environment that they want it to operate for the period that they want to operate as well. So that's really sort of a whirlwind tour of that. In terms of the next steps then, so we're looking to finalize the prototype hardware of the summer. We've got somebody coming in over the summer to help work on part of that as well. So I think we should be in a good position by about September timeframe, which is good, and then complete the documentation design files. One of the things we're also looking at with this is whether or not we look at a sort of industrialization stage. So at the moment, you may not have noticed, but this is all sort of 3D printed. One of the things I'm keen to look at is whether we can use, for example, which we wouldn't use for space, but is suitable for the sort of ground-based environment, is whether we move towards sort of injection molded. But obviously the tooling and the cost of doing that is a bit more expensive, but the quality you get is much better. So looking at whether we industrialize, whether we buy, kits of parts for 100 of them, for example, in order to get the price point down. So we're looking at whether we do that and whether that's the right thing to do, or do we go a sponsorship route, or what other route do we have to try to get that price point down so we can get these into out into the wild, as it were. We will be publishing the design, so as with the open source satellite, making this open source, and really trying to do that towards the end of the year as well. Looking at this batch manufacture as well. So say with EssentialSat, we've built 5, just in the process of buying parts for another 10 or 15. Looking at doing a similar thing with the OSSAT-T and getting to a point where we have a number of them, manufactured and ready to go. Also looking at getting some of the cards out as well. So the onboard computer card, the team have been using some of the STM32 type dev boards. And one of the things I'm keen to do is actually get our onboard computer board out into the community. So those that are working with us on software development will actually then be working on something that's representative of the hardware that we're going to be using in orbit. So that starts to avoid us writing software on a slightly different platform using slightly different peripherals, and avoid some of the problems we then have of porting that across onto the flight hardware. So we move forward to the batch manufacture early 2023, getting it onto the online shop as well, if that makes sense, so we can, so it's openly available. And then in parallel, building up the coursework. And for me, that covers quite a spectrum of things, really, from the basic tutorials and user guides through the intermediate type activities and experimentation, through to some of the advanced topics. So, 4-wheel type AOCS system, for example, and being able to demonstrate the fundamentals of that is invaluable. And then looking at how we might evolve the design. So evolving the examples that we're using, evolving the payloads, and in fact, even looking at maybe there's optional elements that we may look to put in there as well. So, different AOCS system, or adding some other sensors and actuators. So there's a whole range of things we can do. I mentioned that we're working with Cornwall on KernOSSAT-1. So, from my perspective, what would be really cool is to have one of the payloads be a small communications payload, so we can show this picking up data from a buoy, for example, and really making it relevant for how this overall system works, and being able to communicate that. So a whole heap of things, and if any of you got any ideas or requests, then send them through to us, and we'll see what we can do. Okay, so I think I've spoken way too much. I thought it's probably worth just sort of opening up to any questions, if anybody's got anything, or if anybody wants further discussion.
Thanks, John. That was really great. Has anyone got any questions at all?
I guess just an observation. One of the things that's always been really hard, I guess, and we're finding this a lot, particularly with students and things that we're trying to engage with, is actually having that hands-on practical kind of aspect. So I think this would be a really neat way, and hopefully John might help support some of those. Kind of there's a lot of universities and their kind of space flight societies and the like as well, and that'd be really neat for it to kind of play into some of those. So yeah,
I think you're right, and one of the things I'm keen, when I was talking earlier about the good, the bad, and the ugly of what's happening in the sort of the rapid prototyping. One of the things that's used quite extensively on maker type electronics are things like the I2C bus, for example, which is great for taking a couple of boards and bolting them together. But actually, you start taking that and putting that into a spacecraft, you start running into a lot of different issues with noise that you get on the lines, and it's not surprising that quite a few people have had problems when they've tried to use some of those interfaces in orbit. So actually starting to really have a test bed where we can start to talk about some of those challenges and start to sort of guide people in the right direction, I think is quite key.
Hi, we've had a comment from Josh, so that was very good about getting a prop board on board. So that would be fantastic to try. So yeah, great. Any other questions or comments?
And that's not a bad idea either, Josh, actually, because I think what we're going to start to see, and I see Elizabeth's on from NORS, actually. I mean, the days of putting spacecraft in orbit that don't have propulsion systems, for example, I think it's going to start to become more and more difficult not to be able to actively move from debris and things. So starting to get some of those thinking into people's mindsets as they start to put spacecraft together is quite important. Certainly when we started developing the OSSAT, our initial view was we didn't need to put a propulsion system in the baseline platform. Now we're beginning to think, well, actually, or not think, and now we've made the decision that actually we need to have that capability within the baseline platform. Because if we're talking about stimulating the responsible, sustainable use of space, actually having some of that stuff built in from the outset, I think is key.
That's music to our ears, John.
Well, thanks everybody, and I hope that was useful or interesting. I think the next talk that we've got is, in fact, I'm just going to jump back to the slides because I can't remember.
It was me.
It is you, actually, yeah. So the next talk we've got is on the 23rd of June. And Catherine's been doing some really neat work, actually, using a piece of open source 3D software for modeling of solar panel shadowing. So I'm going to look forward to that. Well, I've already seen part of it. It's excellent. So I'd encourage anybody that's interested in that sort of stuff to come along and listen. So that'd be great.
Yeah, demonstration of how to use other non-typical open source material to do a job that you need to do. So yeah, so we look forward to that. So thank you very much, John. That was fabulous. Really informative and real potential for people to get involved, get one of these systems and test out their kit, or for us to test it. So that's really great. So thank you for joining us today. Sorry about the mess ups with the registration. I know what went wrong. It won't happen again. So, but if you are interested in participating in the open source program, there are lots of different ways to get involved. You can register online and to get updates. There's followers on LinkedIn, on Twitter. Also, you can email us to find out more information. You can sign up. You can contribute to some of our projects, which span software, hardware, marketing. You can participate or mentor some of our design-a-thon activities. If you're working on a mission or considering developing a mission, you could be an early adopter and work with us on that. We would love to have other people from outside open source program come in and present, and hopefully we'll manage to arrange that soon. So so if you're listening and think, well, I've got something I really want to talk about related to open source, please do get in touch and we can arrange a slot. We're very happy to share the load. Or you can sponsor us as well. So there are many opportunities to get involved, and we'd love to work with more and more people. So so that's it for now. So unless anybody's got any final questions or comments, I shall close. So thank you very much, everybody, and we'll see you on the 23rd of June, hopefully. Okay.
Thanks, Catherine. Bye-bye.
Thank you. Bye.